Hey, what's up, guys? Yeah, so this is another clown interview question, and probably somebody asked this many times, so I want to like make a video on it. Yeah, if you want to see more interview question, then you can check out my video list. Otherwise, that you can or you want to like learn whatever abstract mathematics or quantum computing or whatever interesting, you can check out. There are thousands of videos in my channel, so it's home all my life that basically lots of like my 10 years, right? Okay. Yeah, so very funny question. So let's dive in. Okay, so there are three random variables x, y, z, and three correlators between three of those are the same. So let's call it row, and tightest bound you can keep row. Okay, so what tightest bound means that we want to know that the upper bound of row or the lower bound of row. Okay, so just recap. So you can basically solve this problem in pure algebraic. Okay, but that's okay. So very simple. Recall the definition. Right, covariance of x, y of two random variable will be just expectation of x, y minus expectation x and the expectation y. The row will be the covariance of x and y and the square root of variance x and the variance y. And the variance x will be expectation of x squared minus expectation x and the square. Okay, and so upper bound is trivial, right? Because I want to make a row to be large, then I can just choose x the same as y, the same as z. Okay, so obviously that when x equals to y, the covariance of x, by definition, this will be the variance. So variance divided by the same variance, take a square root, so it's 1. Okay, so in such case that I can choose everything to be 1. Okay, I can choose everything to be 1. So okay, so I can choose everything to be 1. Okay, so the upper bound of row is 1, right? Because when x equals to y, and I can choose y equals to z, so it's 1, 1, 1, 1. Okay, so the problem is that can I choose row to be minus 1? Okay, so the answer is no, right? So obviously no. Obviously no. The reason is that if I choose, like, let's say I choose y to be negative x, then in this case, that row, the covariance of uh, uh, xy will be negative, right? So which means that the row should be, sorry, so which make the okay, so it's called row, right? Oh, okay, it's called, yeah. So in this case, that okay, let's forget about this. And oh, sorry, it's, yeah, I made it. Okay, it's fine. Yeah, this is covariance, right? This is correlation. Oh, sorry, I'm stupid, but I use row. Okay. So in this case, that your correlation between x and y will be -1. Okay. And if I can choose z to be negative x, then I would say, oh, the correlation between x and z is still -1. But in this case, that y equals z, right? So which means that the correlation between y and z will also be 1. So this is correlation. Okay, then this is covariance. Correlation. Okay, so this tell you that you cannot, right? You cannot choose like everything to be -1. Okay, so there must be some constraint. Okay. Okay, so the naive solution, or basically the common textbook solution, is that you understand this thing called the covariance matrices. Okay, so which you construct a matrices like this. You say, okay, fine. This is where on my x correlation xy, correlation xz, and the correlation y is yx, correlation yy, correlation yz, and the correlation zx, correlation zy, correlation zz. So it's, if you write it down, it'll be 1, 1, 1, row. Okay. And this guy is a positive semi-infinite. or positive. I think it's positive semi-definite. Okay, so you require that all eigenvalue are positive. Okay, which it turns out that since the eigenvalue, the product of eigenvalue will be determinant. So your goal is to show that your goal is just boundless. Okay, and then you can solve it. Let me just quickly solve this. So let's see, right? So determinant of this is 1 minus rho square minus rho minus rho square plus rho square minus rho. So it's 1 minus rho square plus rho minus plus rho cube minus rho square. So it's 2 rho cube minus 3 rho square plus 1. And I know that rho equals 1. This guy is 0. Okay, so this is the condition that I need to solve. Okay, so yeah, I can just divide. I can just try to use the undergraduate division or high school division. So it's rho minus 1, 2 rho square, 2 rho cube minus 2 rho square. So this guy again minus rho square plus 1. Okay, so I know this guy must be minus minus rho plus 1. Yeah, so I get 2 rho square minus rho minus 1 times rho minus 1 is greater than 0. Okay, obviously that I can still decompose this. So this guy should be 2 rho plus 1 rho minus 1 square greater than 0. Okay, so yeah, this is the bad idea to solve this if you are use determinant. Okay, but it's fine. That actually this 2 rho plus 1 will just be sum of this. But never mind that. Yeah, you can like prove this to use the Gaussian iteration. So you can see 2 rho plus 1 is what you want. Okay, so yeah, so this tell you that the 2 rho plus 1 need to greater equal 0. Okay, so rho need to be negative minus 1 divided by 2, right? Because wherever rho minus 1 square is always greater equal 0. Okay, so lower bound is minus 1 divided by 2. Okay, so which is the answer? The answer is bounding. The below answer is negative 0.5, and the upper answer is 1. Okay, so how about n by n? Okay, I will give you the two solutions. So first solution is very simple. We utilize this proof. We utilize this beautiful proof. So let me just quickly give you the another way, right? So the problem for the previous idea is that we solve this eigenvalue just by directly brute force, right? But another way to solve it is very simple, right? So you just stick around, you just stick this and see, oh, you just identity matrices, right? Plus plus 1. So I want to make this to be the same, right? So I can say that I can say, right? So right, okay. So we have the quick way to determine this, to determine the eigenvalue of this. So let me tell you how. So basically, you can see that let's see what's the best. Okay, so let's do this. Let's see what's the best way to solve this question. So our goal is to find the eigenvalue, right? Eigenvalue of this problem. So one way that I would do is that I can see, oh, the sum of this is 2 rho plus 1, the sum of this 2 rho plus 1, sum of this 2 rho plus 1, right? So I can just using the Gaussian elimination, I can just sum over all of this and collect it then into the let's see, into the left. Okay, so I can just do this. So I can get this, for example, 2 rho plus 1 and the rho and the so you can see that I just times minus 1 here, times minus 1 here, and add to the first one. Okay, so 1 rho 1 and the 2 rho plus 1, 2 rho plus 1. Okay, so now I can use Gaussian elimination again, right? So I can just, for fix this line and add times -1 and add through the second and third. Okay, so I get 2 row plus 1 row row. So this guy 0 0 and okay, right. If I add minus times -1 here, then I get minus row plus this. So I get 1 minus row and 1 minus row. These are 0. Okay, so for these matrices, all these are the eigenvalue. Okay. Sorry, when you times -1 row, you become 1 minus row here 0 0. And right, you times -1 here. That yeah, this is this one. And for this one that you get 0 and you get minus row. Okay. Okay, so right, as we know, it's the same as this. 2 row plus 1 row minus 1 squared. Okay, so it's like 2 row plus 1. Right, you know that yeah, so the 1 minus row is not important, right? So it's 1 minus row, 1 minus row. Okay. Yeah. Okay. So yeah. Okay. So that's it, right? So you can just directly see that the answer must be 2 row plus 1, the 1 minus row squared. Okay. So we should prove that the row is greater or equal to negative 0.5. Okay. If you just know the trick. Okay. So for n by n, right, it's trivial, right? You just do this, right? You can just do the like row, right? And you get 1, right? Row, right? And row 1, row 1. Okay, and do the same thing. And let's do the same thing, right? Add it. Okay, so this one times -1 times +1 times +1 times +1 and add to the left. So you get what? You get like n row, n minus 1, right? N minus 1 row plus 1, n minus 1 row plus 1, n minus 1 row plus 1. And row 1 row 1. Okay. Now you times -1 and add it to the second row, third row. Okay, so do exactly the same thing. And all you get is the following, right? You get a -1 row plus 1. And then you get whatever this. But this guy you okay 0, and then you get diagonal matrices. Right? You get the upper triangular matrices. So it's 1 minus row, 1 minus row, up to 1 minus row. Okay, so your solution will be your request. Your request will be your demanding will be a -1 row plus 1 minus row. Okay, so this gives you a lower bound. So row is greater or equal to -1, -1 divided by -1. Okay, so yeah, this is the proof. The one solution that you can just use this and play around with your Gaussian elimination. Okay, but this solution may look like not so natural. Okay, so let me just provide another solution, which is I think is more natural. Okay, so this is very weird. Is that let's consider all this. Let's say I have x1 out of xn, and I know that the correlation between xi and xj are rho. If I derive from j. Okay, I consider the variance of sum over all these random variables. Okay, from 1 to n. Okay, so if I sum over them, then by definition, I will get the I from 1 to n variance of xi plus I from 1 to n, and the j different from I, and the covariance of xi and xj. Okay, this is it, right? So let's see. Let's force. So I can just force the variance of xi to be 1. Okay, just for the convenience. So it's n. And this guy will be row, right? This guy now it becomes row because everything's row, but row with n minus 1. Okay, because you have like n times n minus 1. Okay, and this guy need to be greater than 0. Okay, so this give you rho need to be greater or equal to -1 divided by n minus 1. -1 divided by n minus 1. Okay, so this is a very quick proof. Yeah, but I mean, if you use these matrices, I think it's still a very good answer exercise. Okay, so now the problem is that is the bound tight. So your goal is to construct such solution. Okay, so previously, all I've done is just tell you the bound, right? So hopefully we can find a solution. Okay, so let's consider. So this is a solution construction. So we need to construct. So our goal is to construct x1 of xn. They're all random variables such that their correlation xi and j is negative 1 divided by -1 for I different from j. Okay, so let's start. So let me just start from independent one. So let's say I start from x1 of xn. They're all independent. And for previous that I force this xi should be like hopefully to be 1 for all I for the convenience. And now I can define my yi to be xi minus 1 divided by n, and xj, where j from 1 to n. Okay, we want to make it correlated, right? Correlated. Okay, so first is that one can check the expectation value of yi0, because expectation value of xi is whatever, and this is whatever, but they are the same, right? So it's ui0. Oh, by the way, these are all independent variable, but they are the same. Okay, so they are the same. They are the IID1, but independent. Okay. Okay, so now I want to calculate the variance. So let's see, this is IID. And the univariance. Okay, so let's say the variance of yi. Okay, so variance of y will be a little bit tedious, right? Because you will need to calculate the variance of x plus y. You need to calculate there will be the cross term. There will be a cross term. Okay, so little bit tedious, but you can check it should be like a -1 divided by n squared plus a -1 divided by n squared, which is a -1 divided by n. So you need to check this computation, but it should not be difficult. And then you can compute the covariance between yn and yj. Okay, so this one also you to just use the cross term, right? Just simple calculation. So you get -2 -1 divided by n, 1 divided by n plus -2, 1 over n squared. So this is also just some tedious calculation. So there is. Okay, so you can combine these two and check out your rho will be just -1 divided by n-1. Okay, so this is just a simple calculation, a simple exercise that you can check. Okay, so hope you guys like this video, and see you guys next videos.